So, welcome. Thank you for coming to my talk. So today I want to talk about Quix streams library, which is open source library for real-time stream processing in Python. I want to talk about different approaches to build real-time pipelines, batch versus streaming, different approaches in streaming on its own, and how to actually use machine learning in those pipelines, and pros and cons of each solution. And to demonstrate the solution and kind of connect the theory with practice, I will code it on the stage here from scratch and show you how you can do that by yourself. So I'm Tomas Neubauer, and I'm CTO and co-founder at Quix. And I want to share a bit of a story from my previous job when I was working in McLaren. So in McLaren, I was technical lead, and we were connecting F1 cars to the cloud. So people can build in a factory a real-time decision insight that would immediately tell people in a garage that they have to change tires or change the angle of the wing to get a better performance. And it was quite a challenging use case because the amount of data coming from each car was enormous. Each car produced roughly 30 million numbers per minute, and because McLaren provides ECU to all 26 cars or whatever, you can quickly get it's a massive number. And some of the sensors are particularly high resolution. So some of them goes up to 4 kilohertz, which means 4,000 different numbers per second just from that one sensor. And what we quickly realized that building a database-centric architecture for such a solution would not work because we simply could not find a database that would be able to persist and immediately query that amount of data in production. So we were forced to look around, and we adapted Kafka. And eventually, we connect cars from the garage where we had the receiver into the cloud, and we thought that we succeeded. But actually, a much bigger challenge was ahead of us, because we had a truly cross-functional team that was supposed to work with this data and leverage this technology. But unfortunately, there were data scientists, ML engineers, mechanical engineers for chassis and aero, simulation engineers. And none of them really wanted to use Java and didn't orient it in a Java ecosystem. And they actually wanted to use Python and possibly MATLAB to process the data and get the insight. So we tried to help them, but we find out that the tool set around Kafka and this whole streaming ecosystem, it's really not there. So this is where the idea really started. So I just want to do a quick survey to understand my audience. Who ever used in their work streaming? OK. And Kafka? It's pretty much the same. Fine. So today, I want to build this demo. So I'm going to have here a mobile phone, which will produce telemetry data like GPS location, altitude, speed, and G-force sensor data. And it will be sending it to the cloud, where we're going to have a machine learning model that will detect that the cyclist crashed. And we're going to visualize that in a single-page front-end application in real time. And we're going to build this exactly architecture today. But we need to discuss many things when we start this project. Are we going to use batch or streaming? How are we going to deploy our ML model? And if we go with streaming, what streaming technology are we going to use? Because there are differences. And then I'm just going to walk you through how it actually works and just program it. So before we start, let me just get the streaming working. So here I am in Quix platform, which is a SaaS that is powered by the Quix Streams library. So you get deployment, serverless, code versioning, and monitoring, and everything you need basically to build stuff. And here I have a couple of workspaces that are like a sandbox, which have separated resources. So I'm going to go to IoT phone demo. where I have two microservices deployed. One is the actual single-page application that I discussed, and one is a WebSocket gateway, which is an entry point for my telemetry data for my phone, because Kafka is not really good for such a connection to end devices. It's really an internal tool. So now I'm going to start my application. Now imagine I'm a cyclist, and I'm going to put this phone on my handlebar. So now I'm going to start this, and if the Wi-Fi, there we are, and you can see that we have a green line there. We can click on our start of the pipeline, because this is a pipeline builder, and we're going to build the pipeline that's going to go from left to right. And here you see I'm getting the messages from the phone. You see how much data is that, some explanation how you can send it from different sources. And you can also visualize the data in a, in a live preview. There we are, Samsung S20. And let's say I will get the GeForce data. And if I shake my phone, you see it's going up and down. Cool. So we have a data. Now we want to build what we have discussed here. So how are we going to do that? So first, are we going to use streaming or batch? Well, if we would do a batch architecture, and let's say we would, for example, pick an AWS cloud, we would have some API gateway. We can use AWS service, possibly something else. And we might use Kinesis to send that data to S3 bucket. And then we can use SageMaker to pull the data from S3 bucket for analysis, and then we can label that data and train the model for later use. And when we train that model and we send it to model registry, then what we can do is take that model and use it in some batch framework like Spark, and we can, in periodic batches, load the data that's coming to the S3 bucket, analyze it if there is a crash, if the cyclists actually had an accident, and if they did, well, we're going to send a message to another S3 bucket from where we're going to push this data to AWS Lambda into our front end. Now, obviously, the most obvious problem of this architecture is that it's going to take some time between that data has been produced in that phone, and we are getting event in our front end, because obviously there is a batch framework involved, and S3 bucket is not really a technology designed for real-time processing. The second problem here is vendor lock-in, but again, that might not be a problem for everybody. And the third thing is, again, technology not designed for real-time streaming, like S3 bucket, is de facto here a backbone of this architecture. So if we do streaming, the start is really same. The difference is we're going to send the data straight to the topic in a broker. From that broker, yes, we're going to save the data again to a bucket, and we're going to use that same approach to train the data. So that part is same. When it's different is how we're going to use that model. We're going to use the pickle file we have trained in stream processing service built in Python. We're going to build pub and sub service. We're going to embed this model, and straight in the memory, we're going to flow the data through that model to get the answers. And then if there is a crash, well, we're going to send event to different topic, which then sending this information to our front end. And you know what is cool? We can do this. We can completely avoid a database in our pipeline, which means that we get much better response. There's no delay, but also we're really using a technology for the purpose, Kafka, and we can still persist the data. Probably we won't, but we are not that picky about the time to persistence. We don't have to query this database. We don't have to stress it. It's just for historical purposes what it's made for, and then we use Kafka for the real-time delivery. So you might be thinking, well, to use batch or streaming, it's just a matter of replacing these rectangles in our architecture. But actually, it's more than that, because streaming requires a bit shift in the mindset, because some classical problems have a different solution. So imagine batch. We are collecting points like that until we hit the threshold for the batch size, and then we load it like that. And we actually work with the data. We have that table in our hands, which means to add a stateless operation, a new column, that's easy. And stateful operation is easy as well because we have the data in our hands. In streaming, though, the data are flowing through the pipeline. We are just getting row by row, and we don't know the previous value of the row. So when we get our first row, well, stateless operation is easy. So here we're just computing 3 columns together. That's not a problem. But what if we want to create a delta of a previous row? Well, we don't have that information. So what we have to do, we have to persist the state in this service, in memory, to get that operation done. So the next time we have our information, we just calculate the delta. The tricky part here really is that we need to make sure that this state is always one-on-one synchronized with data and doesn't get lost when we get restarted, or maybe there was some hardware failure in our cluster. And that's what we're going to talk about later, and that's the tricky part. Cool. So let's say we have solved this dilemma. We want to use streaming. Then we want to use machine learning. How are we going to deploy this machine learning into production? Because there are 2 major ways of doing that. One, which is more traditional and being used for some time, is taking that model and deploying it as a microservice with API. And then we're just going to do HTTP requests with input variables, here a GeForce sensor data, and we're going to call the pickle file inside this microservice, and in response, we're going to say it's crash or not. Well, there's nothing bad with that, really. It's just there are some issues with this architecture. First of all, there's a CPU overhead. If you have lots of streaming data, imagine 4 hertz from each phone, thousands of phones. The orchestration of each call is not for free. Secondly, you're introducing delay, which might be a problem, might not be. But the biggest issue, really, is what's going to happen if your service just gets more requests than you anticipated. Maybe the auto-scaling is not that fast enough. What's going to happen? Well, this service will take longer and longer to respond until the time to respond gets longer than client timeouts, and you have disruption in service. That's not great. And even worse, you're losing those requests. So you might lose someone crashing out there, or you might lose a fraudulent transaction in a bank. And that's not cool. So obviously, you can always scale your services, but then you never can predict a peak 1 second from now. Cool. So let's say we want to build a stream processing application. Do we have any options? Well, the 2 major options is, are we going to use pub and sub client APIs of, let's say, Kafka, or are we going to use a full-fledged stream processing framework like Fling? Nothing is silver bullet, as usually in life. So the first option is elegant, lightweight. You have client libraries for all languages. Actually, usually you have more libraries in each language. So for example, in Python, you have 3 or 4 from Confluent, Python-Kafka. There's lots of options. And you don't drag any dependencies like JVM, and the deployment is easy. And actually, it's quite an elegant solution for purely stateless operations when you just process 1 message at a time. So imagine a fraudulent transaction example. There is no context for the transaction. You're just looking at that 1 transaction at a time. When you start doing stateful processing, so you need to look to 10 previous messages, or maybe 100, and you need to do what we have discussed in that diagram before, well, that moment, with this approach, you're going to territory of really hardcore software engineering and a really hardcore understanding of how Kafka works, and it is really not doable to do it just for yourself. It's not wise, I would say. So then you might be tempted to opt for something like Fling. Now, the problem is the moment you do that, the complexity of your system is order of magnitude higher than it was. You have to deploy yet another cluster, like Fling or Spark. You are bringing a heavy JVM dependency to your system. And again, we are back into the problem that we were with Kafka. It's a Java ecosystem, so if you are a Python person and you, for example, want to use PyFling, well, you will quickly find out you are really a second-class citizen in an ecosystem. And then there are some fundamental problems with a server-side architecture of Fling and Spark, which is that you actually don't run your code in your IDE. You don't run it with your Python. You're just creating a function that then you send as a job to some server-side. So you can't debug it line by line like you are used to with normal code. And for example, using profile tools and things like that that developers are used to is just impossible or very hard. So, and that dependency on Java is everywhere. So if you, for example, using PyFling, the Stack Overflow is full of these question and answers about jar files. If you ever tried, you know what I'm talking about. And because you're connecting Fling to Kafka and not your code to Kafka, then you are quite limited to what this connector can do. Which means if your Kafka has some exotic configuration, like, for example, imagine Kerberos, then you're getting, again, to the problems. And just the flexibility is not there, like it is if you're using a client library and you have that power to just do whatever you want. And, well, and then if you opt for a SQL, it might look cool and easy at the beginning, but it's not for all use cases. For some use cases, it's great, and I think better than Python. But the moment you want to go into machine learning, mathematics, statistics, you want to process video, you want to do computer vision, it's really completely out of comfort zone of SQL. And as we heard on the first keynote, this is where people start to abuse the technologies to do something else. So, because when you use SQL to things beyond SQL, you're going to start using UDFs. And if you're doing it with a PyFling, for example, this is official docs from Python, you can see that they run a Python runtime on the side. It's connected to the bridge. It's just not ideal. And when you get exception, well, then it's, yeah, good luck to understanding that. So what we really want, I think, is having something like this. So if something gets wrong in our complex algorithm, we can just find out on what exact line the problem is. And that's going back to our original question. Is there a third way between those two? Well, we believe there is. That's why we have created Quix streams. So we have combined a simplicity and lightweight elegancy of client library with features of Fling and Spark streaming in a Python package. And let's go to a simple explanation what we have done. So if you would use just a client library, like let's say Confluent Python library, and you would read data from topic, and you want to do a stateful operation, what you have to build is, first of all, some concept of streams. You have to split the messages into streams that will then get assigned to partitions. Then you have to parse these messages into, let's say, time series data frames, like in this case. And then you have to create an abstraction between the messages, because then again, you don't really care, you know, how the messages come into. You care about the data in them. And then you have to create a memory state where you're going to persist the data that has been already processed. And because you want to make it resilient, you have to also persist it somewhere. So if you have a restart, you don't lose it. And you have to all synchronize it with incoming data to produce your output while you're synchronizing it with the checkpointing in input topic. And you can see that that's quite complicated. So what we have done is take all of that and we package it into a familiar interface, which is Pandas API. So imagine you are doing rolling window for last 10 minutes on a CSV file in Jupyter Notebook. What are you going to do? You're going to do dot rolling on a column dot mean. Well, you're going to do the same here, except under the hood, we're going to solve it in a streaming fashion. And so we have abstracted all of this drudgery of streaming from the developer and solve it for them. So how this is working? It's a marriage of Kafka, Kubernetes, and Python all working together using the resiliency and scalability features in a tandem. So we're using containers to deploy our Python code. We're using Kafka for resiliency and scalability. And we're using Python because, again, the ecosystem is really unique, especially in machine learning and mathematics. So we're going to build a service that subscribes for input data, call the ML model, and produce the output. And we can scale it because this service is listening to actually smaller topics running in the cluster, distributed over different nodes. So each instance will get third of the data. And this middle part is stateful set running in Kubernetes. So we can, again, scale it horizontally as well. And if there's any hardware failure in Kafka, well, the next leader will be elected, so streaming is ensured. And if there's a hardware failure on underlying nodes in Kubernetes, we get rescheduled to a healthy node, and a Kafka checkpointing system will make sure that our data are not corrupted. So that's how we make this work in production. Cool. So let's do it, and let's basically program what we have discussed here. So here I have the pipeline, and first we're going to go to persistent data because we need to train the model first. So let's say I would get some sessions that happened in the past, and I will now look at the historic data first. So here, something happened in the past. This is 1 minute worth of data. And I can just press this code to get that data into my Jupyter Notebook for training. And it's exactly what we have done in this workbook. So my colleague took a bunch of sessions we have done and loaded it to Jupyter Notebook, where then we did analysis. And we have labeled sessions when we were shaking and not shaking. And now I might be asking what the shaking is about. Well, I can't crash the bike here, so we're going to be shaking the phone today. And so we have labeled the data where we have been shaking and not. We did some analysis, and at the end, we have added some columns. So we inherited some values from raw data, and we trained the TensorFlow model. And then we first checked the training data, then we checked the unseen data to make sure we haven't overfitted the model, and we did the classical historical training that you would do equally if it's a batch system or any other options that we discussed at the beginning. And at the end, we have published that model to model registry. So now, if I go back to this pipeline, I'm free to start building that pipeline and process it. So first, I'm going to add a new node, and I'm going to add a transformation, because what we want to do now is transform this data from a telemetry coming from my phone to are we crashing or shaking or not. And this is our, I would say, microservice generator. So the idea is that there's an open source GitHub monorepo where all the templates and services are available. And this SaaS synchronize the main branch and allow you to configure the whole repository for your infrastructure and your problem to solve. So here I'm going to do that detection, and I have all the environment variables preset. So if I press here and give it a name, so detection, and I just say I want to get data from the phone topic into Fleet Console and save it as a project, now it's generate a Git project that's just going to work out of box. And I have two options how I can develop this code. I can either use this web IDE, which is now in Kubernetes, creating a pod with all the dependencies I need to develop in Python, or I can check this through the Git interface and use my favorite IDE to do it. So here, I can just quickly show you if I put here a print that is working. Cool. So if I press run, this would print the messages coming from my phone. There we are. You see, we're getting data. So that's how it's easy. And now it's just about the Python. OK? So we can do a magic. So I'm going to stop this and clone it to my PyCharm, which I actually done already. So here is the empty template. And now let's build some processing. So first, we're going to get a streaming data frame here. So you might be thinking, well, what is the streaming data frame? It is an object that looks like Panda DataFrame, but obviously under the hood, there is no data. It's just virtual. There are data flowing through this frame, and there's Python transformation applied to it. So here, I can do, for example, I want to just these 3 columns. Again, you would do exactly the same in your Jupyter Notebook. And then I can just do something like this. Print header to see what we're getting. And then let's just iterate this like that. Cool. So if I run this now, we're going to get data streaming rows to our frame into this service. So there we are. And if I go up, there you see the header. We have 3 columns, 3 dimensions for sensor data. Cool. And it's streaming. So if I go to the bottom, you see that it's going down. You see some gaps? Well, this is because sometimes the phone is not sending GeForce data, but, for example, GPS location. So what we're going to do is, first of all, filter that. So when GeForce X is not null, and then let's create a new column called GeForce Total, because that's what the ML model is going to expect. There we are. And again, we're going to do classical thing. So, and here we're just going to do 3 columns, and we're going to combine them together. There we are. And what if we want to look at data a bit from bigger picture? Because one point might be just, some noise in our data. This is exactly the moment where we're going to create a stateful operation. So here, I'm going to create another column called GeForce Total 10 seconds. And I'm going to use this column as an input and do something that everybody that use Pandas have to remember. And this is the beauty. I don't have to learn a Quix way of doing things. I just use my skills from my previous career in a batch to build streaming applications. So now, if I just make the columns a bit smaller, so it will fit. Let's start this. There we are. So if I go to the top, we have following columns. So the last one is the rolling window. And now, if I start shaking, you will slowly see going that last column up, because we are generating more g-forces in the last 10 seconds data. If I put it back on a table, it will go slowly down. And this is now a stateful operation that library, Quix library, will make sure it's resilient and it's going to scale to multiple replica. So now the last thing we want to do here is apply the model. So here I have some code I'm just going to copy-paste. This one is how to load from model registry the actual model. That is Azure Blob Store in our case, but it will work similar to S3 bucket. And this is the method. Oh, this is how we're going to call that. And now what I'm just going to do is create yet another column, which is going to contain our information. So here we have a shaking, and that will be apply predict. Cool. So what is missing now is the last line of code to make this application working. We need to send this information not just to console, but to somewhere else so our application can visualize it. And that's going to be another topic. Remember that diagram with input and output? Well, here, which we are just going to do following. Await, output stream, write, row. We are done. So now, I'm going to press run. And first, we're going to check if it's working in a console. And then we're going to check our application if it's actually working there as well. So, there we are. So there's a 0, which means no crash. Okay? And if I now shake, yeah, you see, there's 1. So the shaking was detected by a machine learning model, and it's been sent. And now, if I go to our pipeline here and open this, this is getting data from the phone, and if I shake, you have alert coming from the machine learning model, completely real time here. So if you would be watching here a fleet of cyclists, we would get in the map, as you can see, alert that this cyclist crashed, and we can obviously move it to alerting system, etc. And all is happening with roughly 45 milliseconds delay from the phone to the cloud and back to the phone or front-end application. So it's really real time. Now, the last bit here is how I can make this code that you see here run in production. Well, that's quite easy. So first, I'm just going to go to Git, and here I'm just going to stage the main PI file, and I say version 1. And then we're using Git tags to connect the code in production, so we can call this version 2. And if I push it and go back here to that project, I can deploy it with a single button. So I say version 2 service, 2 gigabytes of memory, 1 CPU, how many replicas, if it's stateful processing or not, and if it's public access for querying the state, or possibly if you have a website application. And I press deploy. And what it's going to do is going to use a Docker file that we have provided in that service that you can obviously change. And it will build it into Docker image. Then it will use Helm chart provided to deploy that container into Kubernetes and give you logs and monitoring for that. So for example, here we have the front-end application. You see the logs. You see the CPU. You see the memory. And basically, you as a data person are available to do all the steps you need for your work from nothing to staging, let's say, even in small companies, even to production. So I hope that it was clear and you like it. Now, you can obviously try this open source library on GitHub. And if you like it, you can give it a star. And if you have any questions, I'm here. Or here is my colleague, Lee. He's ex-Confluent VP of Sales in Quix. So yeah, we are here to answer any questions. Thank you very much.
What delivery semantics do you guys currently support?
Yeah, so the library, it's a bit focused on telemetry time series data. So there is a codec in protobuf and JSON for sending numeric, string, and binary data, like video and audio. And then there is a classical event payload. We have on our roadmap Avro as a support. And yeah, so.
Yeah, that's awesome. But I was like asking more about the actual like delivery semantic guarantees. Like
delivery semantic. Yeah. Okay, sorry. So you can switch between exactly once or at least once. And the way how it works is that the state is persisted, not every message, but every time there is a checkpoint to the Kafka. Mm-hmm. And then there's a watermarking for that. So the way how it works is that when you get restarted and you have at least one semantics enabled, we will basically start from the checkpoint in a Kafka topic, and we would load the state from PVC in Kubernetes for that exact moment. So you're basically starting a line one-to-one. And the advantage of that solution compared to, for example, Kafka Streams approach is that there's no pollution in your broker if you have a lots of state. So we don't send the state to topic. And secondly, you do that every 20 seconds, every 30 seconds. So if you have a really big influx of data, you're not hammering the disk that often.
Awesome. Thank you.
Cool. Well, if you have any question later, we are here today, tomorrow. So enjoy the rest of the conference, and thank you for coming here.